Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study springs. What is the types of springs? What are the types of springs? And how the springs are useful? What are the purpose of springs? And what is the deflection of the spring when the axial load is acted on closely helical coiled spring? The Bloom course outcome and Bloom's taxonomy related to here it is that is the course outcome is number 6. Here make use of the concept of torsion and buckling of thin shells, spheres, etc. to determine the stresses at various points of geometry. The level of Bloom's taxonomy is the applied level here. Now here consider the purpose of the springs. What is the introduction of the springs? Springs are the elastic bodies which are used for absorb energy due to resilience, and the absorbed energy may be released as and when required. A spring which is capable of absorbing the greatest amount of energy for the given stress without getting permanently distorted is known as the best spring. There are two types of spring broadly. Number one, laminated or leaf spring. Another one is helical springs. Now here if we consider the spring in this, when the load is acting, axial load is subjected here, it is absorbing energy. So the absorbing energy and also without getting distorted the structure of the element. That is the speciality of the springs. Now here, if we consider the laminated or helical spring, if we consider the function of this laminated spring is that to provide comfort to the passengers by minimizing the vertical vibration caused by the non-uniformity of the road geometry. So the load will be subjected here in this direction. The load will be acted here. So what will happen? This helical spring, this leaf spring or laminated or leaf spring, gives the comfort to the passengers by minimizing the vertical vibration caused by the non-uniformity of road geometry. So it gives a comfort to the passengers by absorbing. It also stores the strain energy, as I here absorbs energy due to resilience. Yes. Now, what are the parts consists of this leaf spring? It is an eye end, the master leaf. The master leaves is the center clamp, is the camber, and the span between two eyes are the 2L, the graduated leaves. So these are the under rebound clip is considered. There are two rebound clips. Now, which material is used for leaf springs? The material used for leaf springs is a plain carbon steel, and the plain carbon steel is having that is 0.9 to 1% of the carbon, and these leaves are heat treated after the forming process. Here forming process takes place and heat treated. So the heat treatment of this spring steel products or plain carbon steel, also another name is spring steel products, having greater strength, and because of the greater strength it is having a greater load capacity without getting distorted, and a greater range of deflection and better fatigue properties. The fatigue strength is high, and also deflections, greater range of deflections, and more greater compressive load capacity. The compressive loads will act. And the material made of these leaf springs are plain carbon steel, that is known as the spring steel. Now here this type of the way of these leaf springs are used in the case of four-wheelers and heavy load vehicles and army vehicles. This is the position, the location of the leaf springs is the camber position, and you can see the rebound clips. These are the rebound clips, keeps together all the leaves. These are the leaves means the flat plates. Okay, gradually. The master leaf is the starting one. This is the eye end. Eye end is clamped. So the camber. So these are the loads drawn such a way that what will happen? The load acts the here, okay, and it help us support, then it completely. Now you can see the load acting here, how it will be subjected to the deflection here. Now when the leaf springs are made here, how the you can see the effect on the deflection of the leaf springs. And which next, coming to here, coming to helical springs, there are two types of helical springs. One is a closed coil helical spring, another one is open coil helical spring. This is the closed coil helical springs, okay, and it is the open coil helical spring. This is the open coil helical spring and it is the closed coil helical springs. So in the closed coil helical springs, the gap between, you can see the pitch is low in the case of closed coil, the pitch is more in the case of open coil helical springs. Now here we are considering, we are finding out the deflection of deflection of the helical coil spring when the load is, what type of load here, the axial load is acting on the spring, on the helical coil and the closed coil helical spring. Now here the number of turns, these are the turns of the spring consists of, there is the pitch P and D is the diameter of the wire, coil wire, where capital R is the mean radius, that is center from the outer, and axial load W is acting on that. So closed coil helical springs are the springs in which the helix angle is very small in comparison to open coil helical springs, or in other words, the pitch between two adjacent turns is very small. And a closed coil helical springs carrying what type of load? Axial load. Axial load, it is a shown figure. As the helix angle in case of closed coil helical springs are small, hence it is a small helix angle, the bending effect on the spring is ignored. Because the helix angle is small, the bending effect on the spring is ignored, and we are assuming only purely torsional stresses. Purely torsional stresses. One of the side point here, when the load acts on the spring, okay, when the load acts on the spring, there are two effects will be there. One is due to shear, direct shear, another one is due to torsion. So direct, that's the total shear stress equal to, due to direct shear stress, that is shear stress, that is shear load by area, that is F by A, and due to torsion, the torsion means torque TR by J, torque times radius by J, because tau by R equal to T by J. From that, tau equal to T R times J. So the total shear stress in design of the springs, the total shear stress equal to shear stress due to torsion, that is T R by J, and also direct shear stress F by area. Now in the case of, we are going to study here the solid mechanics, we were considering closed coil helical spring. So the helix angle is small, such a way that the bending effect is ignored, and we are considering the torsion, the shear stresses, pure torsional stresses. Now in order to find out the shear stress, the torsional stress induced in the wire, the maximum torsional stress, we have to consider that let a small d is the diameter of the spring wire and small p is the pitch of the helical spring, and n is number of coils. How many coils are here? 1, 2, 3, 4, 5. 5 coils here. And R, what is the capital R? Is for mean radius of spring coil. And W is the axial load on the spring. What is C? Is the modulus of rigidity. C is the modulus of rigidity. Tau is the maximum shear stress induced in the wire. Theta is the angle of twist in spring wire. And delta is the deflection of the spring due to axial load. And where is L is the length of wire. These are the various parameters we considered in order to derive the expression of the shear stress and also deflection induced in the wire by the axial load. Now here let us go for now the twisting moment on the wire. What is the twisting moment because of this axial load? Twisting moment, that is equal to T equal to W times R. Now we know the twisting moment from the theory of pure torsion equation. that is T by J equal to tau by R. From that, or C theta by L. By using these two equations, we calculated the torque T equal to tau times J by R. That if you substitute what is the J for Y, that is pi d power 4 by 32. Pi d power 4 by 32, R equal to d by 2. If you substitute, you will get it T equal to pi by 16 times tau d cube. We know that T equal to by axial load, twisting moment, or turning moment, that equal to axial load times radius, that is capital R. Now substitute here, equate equation, both are torques, so twisting moments. Equation 1, equate both the equations, that is W times R equal to pi by 16 times tau d cube, where tau is the 16 W times R by pi d cube. This is the shear stress. This equation gives the maximum shear stress induced in the wire. What is the unit for the maximum shear stress? Weight is W, that is newtons. R is in millimeter. It is in d cube, millimeter cube. Get cancelled square. That is Newton per square millimeter. Unit for shear stress is the Newton per square millimeter. This is the shear. The equation gives the shear stress, maximum shear stress induced in the wire. Now we got the shear stress induced. Now we want a deflection, the deflection of a spring, the expression for deflection of a spring. Okay, what is the expression for deflection? How to make it? Now, the length of one coil. What is the length of the one coil? How can we know? That is a pi d, that is radius. Length of one coil pi d, that is pi d or 2 pi r. 2 times, that is circumference. Now total length of the wire means the circumference times number of coils. What is the number of coils? Length of the one coil times number of coils. That is L equal to 2 pi r times n. That is length of the one coil means this is the one coil. What is the length of the one coil? Circular. If you see the top view, we know the d, that is becomes pi times d, that is total circumference comes. How much? What is the total length? The number of coils if we consider it. Each circumference should be there. That is L equal to 2 pi r times n. Now here, as the every section of the wire is subjected to torsion because of the axial load is acting on the wire, the strain energy stored by the spring due to torsion, that is equal, that is strain energy stored by the spring equal to U equal to, that is due to torsion, that is tau square by 4c times volume. Yeah, actually sigma square by 2u times volume we have studied. Tau square by 4c times volume. Now what is the volume here? The volume equal area times length. Now what is the tau value? The tau value derived as 16 times W times R by pi d cube. 16 times W R by pi d cube whole square, that tau square by 4c, 1 by 4c times pi d square by 4 area times length 2 pi r n. After simplification, we'll get how much? That is 32 times W R square by C d power 4 times R n. That is 32 W R cube, W square R cube n by C d power 4. This is the strain energy stored by the spring. Now, what is the work done on the spring? Whatever energy stored in the spring, the work done on the spring equal to average load times deflection. That means of W times deflection, of W times delta. Now equate that deflection, work done on the spring, and the strain energy stored in the spring. That is of load into deflection equal to 32 W square R cube n by C d power 4. Cancel W and delta and 1 by 2 comes here. Then it goes to 2 to R side, that is 64. Delta equal to 64 W R cube n by C d power 4. Okay, and this is the deflection, expression deflection. Delta equal to 64 times W R cube n by C d power 4. So this is the expression for stiffness of spring. Now, this is the expression for deflection of the spring. Now, what is the stiffness of the spring? If we know the deflection, the stiffness S equal to load per deflection, W by delta. What is the W? We know the W, axial load. What is the delta? Substitute this expression, that is 64 W R cube N by CD power 4. Then W get cancelled. Then what will happen? CD power 4 by 64 R cube N. This is the expression for stiffness S. CD power 4 by 64 R cube N. Again, once again, we want, very important here it is, the deflection, expression for the deflection. That is 64 W R cube N by CD power 4. Now 64 W R cube N by CD power 4. What is the W? Axial load. Okay. And what is C? Where C is the modulus of rigidity. Where C is the modulus of rigidity. What is the D here? D is the diameter of wire. D is the diameter of wire. Where N is number of coils. What about R? R is the mean radius of the spring. R is mean radius of the spring, or mean radius of the coil. So here, this is the, in this manner, where delta is the deflection. What is the unit for deflection? The unit for deflection is deflection is millimeters or meters. So in this manner, we have to derive the deflection. Deflection comes from where? The expression for stress, shear stress. The shear stress should be known. From the shear stress, we get the deflection because strain energy stored. So here in this derivation, or in this expression, we derived the expression for shear stress and the expression for deflection and also expression for stiffness. So if we calculate the shear stress, we can calculate the deflection expression, and if we calculate the deflection expression, the stiffness expression comes very easily. That is a load per deflection. Now here we consider only that closed coiled helical spring. Okay. Next, let us how to apply these derived expressions in problem solving. How to solve? Let us begin with, here a closely coiled helical spring is to carry a load of 500 newtons. Its mean coil diameter is to be 10 times that of the wire diameter. Calculate these diameters if the maximum shear stress in the material of the spring is to be 80 Newton per square millimeter. 80 Newton per square millimeter. So, what to be calculated here? We have to calculate capital D and small d. Calculate these diameters. What are the diameters, sir? Mean coil diameter and the diameter of the wire diameter. These two to be calculated. This problem was given one of AMIE exams, associate member of Institution of Engineers India. Now here, let us, what is the data is given to solve the problem? That is a load on the spring, that is the axial load is 500 newtons. The next one is mean coil diameter, capital D equal to 10 times the diameter of the wire, 10 times D. And one more parameter is given here, the material of the spring, that is called modulus S. What is if the maximum shear stress? The maximum shear stress was given, that is tau equal to 80 Newton per square millimeters. So how to calculate? We know the relation, what is the shear stress? shear stress versus mean diameter and capital D and small d here. That is the relation is tau equal to 16 times WR by pi d cube. Substitute in this formula what is the W, what is the R, and what is the Y diameter. Now tau equal to 80. 80 equal to 16 times W, 500 newtons. Capital R equal to capital D by 2 times pi d cube. Why? We know that capital D equal to what is the 10 times D. 80 equal to 16 times 500. Capital D is equal to 10 times small d by 2 times pi d cube. So we can calculate here D diameter. That's what here we do. So what is the D equal to? D square equal to 159.25. What is the D value? The D value is 12.6 millimeters. After knowing the D value, we know the relation between this Y diameter. We want a mean diameter, mean radius. What is the capital D equal to 10 times small d. That is 10 times small d is 12.6. That is 126 millimeter. In terms of centimeters, that is 12.6 centimeters. So this is what two objectives are calculated here. The mean coil diameter is 126 and the diameter of the wire is 12.6 millimeters, and the relation between here mentioned that is 10 mean coil diameter equal to 10 times the wire diameter. 10 times the wire diameter. In that manner we calculated here, we solved the problem by using, here we applied only shear stress. Now if we change, now very important here, now just let us discuss 16 times the formula of shear stress, 16 times WR by pi d cube. So the relation between the shear stress and the load and the mean radius is proportional WR, whereas with the mean coil diameter it is inversely proportional to. So if you draw the graph, the mean coil diameter, if the mean coil diameter increases, if the mean coil diameter increases, the shear stress decreases, the effect of the shear stress decreases. So that means the diameter of wire is more for the same axial load, for the same of mean radius, or for the same of coil diameter, coil radius, and the same for the same axial load, the shear stress can be reduced, the action of the shear stress can be reduced by increasing the value of the coil diameter. If we increase the coil diameter or the Y diameter, then the shear stress will be reduced. Shear stress will be reduced for the same axial load, W and R. W should be for the same axial load and WR. Now here one more thing. Tau equal to, what is WR here? W means torque, 16T by pi d cube. From this relation you can see how the torque equal to comes. Torque equal to pi by 16 times tau d cube. We got it here, this equation. From this equation only we got the shear stress value. Tau equal to pi by 16 times. If you remember here, T equal to tau times pi by 16 d cube, right? Now from this shear stress we want, this is the shear stress formula we derived in the case of pure torsion formula. From that we derived here the relation between T and J. Here tau by R equal to T by J comes from this. Now T equal to what? 16T by pi d cube. What is the T here? Torque T in the case of the springs, W times R. That is the formula here. W 16 times WR by pi d cube. How this formula came out? From the equation of the torsion formula which we got here. Okay, tau equal to 16 times WR by pi d cube. Alright. So here we are, that is the shear stress equal to 16 times WR by pi d cube. Now what is the W here? The unit for W is the newtons. What is unit for radius? As we have as discussed here, there is the mean coil diameter, mean coil radius, there is millimeter. What is the D? Diameter of the wire. What is the tau? Shear stress. So in that manner, we can say that for the same data, if we consider the diameter increases, the D value, if we give it, if we know the values of axial load, mean coil diameter, and the diameter of the wire, we can calculate the shear stress directly. So these are the problems, direct solving problems, provided the formulas are known clearly. So this formula here, if we understand the shear stress developed inside the material or inside the closely coiled helical spring, this formula is derived from the formula of torque T equal to tau times pi by 16 d cube. This is for solid. The spring wire is the solid spring. It's not a hollow coil, hollow wire. It's the solid wires. So this is in this manner we solved. So in this session we solved what we discussed. What are the types of springs? What is the importance of springs? There are two types of springs. One is leaf spring, leaf or laminated spring. Another one is coiled springs. Again, coiled springs are two types: closely coiled and helical open coiled springs. So helical springs. Again, we discussed here only deflection. We derive the expression of the shear stress developed in the closely coiled helical spring, the deflection expression, and the stiffness expression of a closely coiled helical spring. And we solved one problem, one model to apply the shear stress, expression of the shear stress, to find out the shear, to find out the dimensions, that means mean coil diameter and the diameter of the wire. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.